Okay, hello, welcome everyone to Reinforcement Learning Seminar. It's our pleasure to have Nan Jiang with us today. Nan has done a lot of great research in reinforcement learning theory. Nan currently is an assistant professor of computer science at University of Illinois at Urbana-Champaign. Before that, he was a postdoc at Microsoft Research, and also before that, PhD student from University of Michigan. So Nan's research is basically in theory of reinforcement learning and mostly focusing on how to design more sample efficient algorithm. He has done a lot of great research. Some of the topics that he has studied has been on the sample complexity of exploration under function approximation, of policy evaluation and selection, and batch reinforcement learning. So yeah, please join me in welcoming Nan. It's all yours now.
Thanks, Amir Masood, for inviting me to give the talk. It's my great pleasure to virtually visit Vector Institute. Hope at some point I will be able to visit you guys physically. Okay, so today I'll be talking about some of my group's recent work on batch reinforcement learning. Okay, so let me just start by giving you like a broader context of why I work on this, but like what's the problem roughly speaking, and why do I think it's very important? Okay, so we know that in reinforcement learning, one of the core problems is to learn good decision-making strategies in highly complex dynamical systems. For example, in standard benchmarks, you see like interrogations with high-dimensional pixel observations, which give rises to many different challenges. For example, it will require you to use complicated function approximation schemes, such as deep neural networks, to generalize across the large state space. Okay, so with this as the ultimate goal, we can look back and see how we have been approaching this goal, historically. So it turns out that the dominating approach that we've been adopting in the development of reinforcement learning is that, okay, we know that this ultimate problem is quite challenging. So we want to first simplify it, study the simplified model, and see if we can extend the approach to the more complex situation. And so this gives rise to the study of so-called tabular reinforcement learning, where we simplify the environment and focus on problems where there are a small number of states, a finite small state space, and the name tabular comes from the fact that in these kind of environments, the functions of interest can often be written down using a tabular representation. And what we do is that we develop algorithms for the tabular case, extend them naturally to the function approximation case, and see like what kind of assumptions we need to make to analyze these algorithms and provide provable guarantees. Okay, so that's in a nutshell, that's what the RL field has been mostly doing, especially on the theory side. Okay, but I would argue that there's an alternative way to simplify the problem and look at whether we can approach the simplified problem. And in this approach, instead of simplifying the dynamical system itself, what we do is that we keep the dynamical system intact, still very complex with high dimensional state or observation spaces. But instead of thinking about complex function approximation schemes, we can think about simpler hypothesis space, right? So instead of neural nets, you can think of, say, linear function approximation. But I would say like even that is very complicated. And I would be happy to think about something like a finite and small hypothesis space. And we can ask ourselves, in this kind of simplified scenario, do we know how to do RL in this case? Okay, so and today's talk, I will be focused, in RL, there are many different sort of modes or models of learning where sometimes you can have online interactions, sometimes you only have like offline access to data. So in today's talk, I'll be focusing on the paradigm called offline reinforcement learning with value function approximation. Okay, so this is the scenario where you can't directly interact with the environment, but only have access to a pre-collected data set, and you want to use it to approximate the so-called value function of the problem, which I'll define later. But hopefully that concept is, at least many of you have heard of the concept. And the reason that this paradigm is very important is because, so first of all, it's a very basic and prevalent paradigm in reinforcement learning. It's also directly related to the empirical success of deep RL, right? Because, for example, if you think about the popular DQN algorithm, essentially it's an offline value function approximation algorithm, coupled with some exploration heuristics. So the success of the algorithm really highly depends on the success of the offline learning module. This offline RL setting is also very important to real-world applications because in many important applications that we hope to apply RL to, such as conversational systems, customer relationship management, online education, medical applications. So in many of those environments, especially when human users are part of the dynamical system, it's almost impossible to come up with good simulators, and you really need to rely on data from the real system. And also in those systems, because human users are part of the environment, you can really collect data by taking arbitrary decisions online. There's safety, ethical, and financial considerations. And I think there's an increasing consensus within the RL community that offline RL is a really, really important paradigm for applying RL in these kind of applications. Okay, so but back to what I'm gonna want to talk about today. So what I want to talk about is really as I mentioned, I want to simplify the problem, the RL problem, down to the sort of minimal level and ask whether we can solve that kind of questions. And to give you a sense of how simple I'm talking about, I want to give you a, let's first make an analogy in the supervised learning set, right? So in standard supervised learning, what you have is, XY pairs. Let's say you're doing regression. You have X, the features, Y is the real value label, drawn from some ID, drawing an ID manner from some distribution, okay? And what's the simplest possible question you can ever ask in supervised learning? Well, I would argue that you can ask, if I have two hypotheses, H1 and H2, right? So it's like two curves. I can ask which of the curves better fits the data, right? And this is very simple, it's naive, and everyone knows how to solve it, right? You just evaluate the error, the loss of each curve on the data you have, and pick the one that gives you the better, the smaller loss. Okay, so, and also, essentially, this is what we do every day in supervised learning practices, right? Because this particular procedure is essentially holdout validation, right? So when we do hyperparameter tuning in supervised learning, we run different training algorithms with different hyperparameters. They produce different hypotheses. We take that finite and small set of hypotheses and just evaluate their training error on the holdout data and pick the best one, okay? And we have some reasonable theory about it, like Hopding plus union bound gives you a decent theoretical understanding of what's happening. This is also gives us it's also alluding to the principle of empirical risk minimization in training, because in validation, because of the finite hypothesis space, there's no difficulty in optimization. So we can just exhaustively enumerate the functions to do optimization. But what we do in training, roughly speaking, to a first order approximation is not that different, right? So we're just minimizing training error up to regularization terms and so on. Okay, so this gives you a really rough picture of what's the simplest possible question you can ever ask in supervised learning and what lessons and what principles we can learn from it. So what I want to do is that I want to ask the analogous questions in reinforcement learning. And perhaps surprisingly, the answer, we actually don't have good answers to the questions that can be asked in this very minimal and simplest way. Okay, as I mentioned before, I'm not going to simplify the environment. I'm still going to consider highly complex, high-dimensional state space, systems. Just like in supervised learning, on the left-hand side of the slides, in this supervised learning paradigm, you never made assumption that the data has to be generated in a very, very simple and naive way, right? So we still have this complex environment. We're in the offline setting where there's some pre-collected data, state action reward next state from the environment. And we have candidate functions. So here I'm also making, taking the setting, the simplified setting where I say, okay, I only have two hypotheses that I need to worry about, say F1 and F2. They're functions of the state action space. Okay, and in RL, a lot of the times the goal is to approximate the so-called optimal Q function or Q star, which I'll define later. And maybe I can just, to make our life even easier, let's say one of F1 and F2 is Q star. Okay, you don't know which. And what you want to do is that you want to figure that out from data, right? So this is the analogous question of what I've just asked in the supervised learning setting. And turns out that as simple as this question seems, we basically didn't know how to solve it. Okay, so and by didn't know how to solve it, I mean really like there's nothing that really works without additional strong assumptions. And if you think about it, this question not only is theoretically has foundational importance, it's also super important in practice, because if you don't know how to solve this question, how are you going to do hyperparameter tuning offline RL, right? So say you run offline DQN on your batch data, you generate a bunch of Q functions. Okay, you prepare the holdout data, and you look at the functions and look at the data, and you don't know what to do. Okay, to select which function is the best one that you want. And indeed, it turns out that hyperparameter tuning is a big open question in offline RL. And we'll also talk about something about what's the implication of this question on training. Okay, so that's roughly the problem I'm going to talk about today. And but so far everything has been very informal. So I want to take a little bit of time to just to use standard notations to set up the problem a little bit more formally. Okay. So as hopefully many of you are familiar with, we're going to use the standard markup decision process formulation, where if the agent interacts with the environment, it will observe a state at each time step, ST. And here I'm assuming that the state space is very large, that you don't want to pay any dependence on the size of the state space. And the agent will choose an action. For now, I'm going to assume that the action space is finite small, but as we'll see, it's not necessarily, we don't necessarily need this. Okay, and then after you take the action, you receive the reward RT according to the reward function, and then you transition to the next state, essentially ST+1, given according to the transition dynamics P of the environment. Okay, and decision-making strategy is often described by a policy pi that maps states to actions. And how good a policy is often determined by JPi, the expected return of the policy under the initial state distribution D0. Okay. And some of the key solution concepts in RL, one of them is the Bellman equation or Bellman optimality equation that says that there's the so-called Q star optimal Q function, which is the fixed point of the Bellman optimality operator T, which essentially do a one-step backup of any function that if you give the function to the operator. And why is this important? Because this Q star function basically tells you if you start from some state action pair, what's the optimal long-term return you'll be able to get. And once you know that function, acting simply greedily according to this function would give you the optimal strategy, pi star. Okay, and there's also a somewhat another important concept called the occupancy, which describes, given the policy, what kind of state action it will visit, but it won't be super important for this talk. Okay, so this is a very quick review of the basic MDP terminologies. So let's turn to the learning problem that we're interested in this for this presentation. So in the learning problem, we don't directly can interact with the MDP, but instead we have this data set, right? And to simplify things, I'm going to assume the standard so-called offline sampling protocol, where there's some state action distribution mu, which you can sample IID SA pairs from. So I'm going to call this mu the data distribution for the rest of the talk. And once you sample each an SA, the reward R and the next state will be generated according to the environment dynamics. Okay, and what you get is a bag of data of this like 4 tuples. Okay, so and also for simplicity, we don't really need this, but for now, let's just assume that mu is fully supported on the state action space.
Maybe just a quick question. So here,
yeah, Pascal, go ahead.
For the data set, so you are literally assuming that we just have 4 tuples. We don't have trajectories, right?
Yeah, we don't have trajectories. We have four tuples. Yes. Great question. So though, I mean, some of the, I'm gonna first, so once I set up the problem, I'm gonna first describe something that doesn't work, okay? But among the things that I describe as doesn't work, some of them require trajectory data. So
yeah, because if we have trajectories, many things become easier.
Yeah, you're right. But it turns out, so the thing is that trajectories are very, very useful. Trajectory data are very, very useful when you're doing on-policy RL, right? Because you can do Monte Carlo. It turns out that I'll actually get into it in a minute, but Monte Carlo becomes important sampling in the off-policy regime, which gives you exponential variance. So in the offline regime, the entire trajectory data is not that useful, but you're right. It could be that in some cases, the difficulty of the problem may be mitigated by considering entire trajectories instead of just these like chopping up them into tuples. But in this particular problem, we don't find it to be very useful.
Okay. Well, I mean, if I had entire trajectories, I could imagine that given a state, then I just add up all the rewards and the rest of my trajectory. And that's my estimate of some value function.
Exactly. But that would be the estimate of Q pi of the behavior policy, right? It won't be the estimate for the optimal policy.
That's true. Okay.
Yeah.
Okay,
that's why I'm saying like this is a difficulty, a difference between on policy and off policy learning, right? So on policy learning, you only care about evaluating how good the policy you're actually running is. But here we're considering off policy problem.
Okay.
Yeah. Yeah, I actually get to that related point in a few slides. Okay, so and as I mentioned before, we're going to consider the setting where the simplification, the major simplification I made to the RL learning problem is that instead of asking you to learn using say a neural network, I'm going to give you only 2 candidate functions, right? F1 and F2. Showing either blue and red on the figure. And I also tell you that one of them is Q star, okay? We're gonna be able to handle approximations, but for now, let's just say one of them is exactly Q star, okay? You just don't know one, okay? And you have this nice data set, okay? And just need to figure it out using the data set and these 2 functions. And I don't want you to make further stronger assumptions on other things you can have access to. Okay, so this seems very simple, right? So, but it turns out that we don't quite do, as I mentioned, we don't quite know how to solve this. And but before I tell you like potential solutions, let me first like lay down some minimal requirement on what do we mean by solving the problem, right? So if I give you an algorithm, how do you decide whether this algorithm is satisfactory or not? So I'm gonna give you like 2 requirements. First, the algorithm should be consistent, right? So if I give you an infinite amount of data, you'd better like figure out which one is Q star for me. Okay, so this is number 1. I think this is really minimal, right? Excuse me. Number 2, when I want the algorithm to be scalable to really complex problems, right? Meaning that if I only give you a finite sample, you use the sample set to estimate some quantities, right? I say that your algorithm should never estimate something whose variance or estimation error scales either with the number of states, which means that you're taking a tabular approach, which doesn't scale, or exponential in the effective horizon of the problem. As we'll see, there are existing methods that gives you these kind of estimation errors, but because of this exponential variance, it's also not scalable to long horizon problems. Okay, so clearly, like if an algorithm satisfies these 2, it's unclear whether that's a good algorithm or not. But if an algorithm doesn't satisfy either of this, it's clear that it's very problematic. And I want to say that when we talk about the estimation error or variance of the algorithm, we can certainly like we should certainly accept some like polynomial dependence on 1 over epsilon, because even in supervised learning, you still have 1 over epsilon square dependence on the sort of suboptimal error. Okay, so but even with just such a simplified setting with this very, very simple requirements, it turns out that for a long time, we first didn't know how to do it, and second thought that this is impossible. Okay, and we actually formalized this, somewhat formalized this as a negative conjecture in a paper in 2019. And at that time, I think I 100% believe that this is just impossible and there's no way that we're gonna solve it. So why? Okay, so next, let me tell you a little bit of like, what are the natural existing approaches that everyone has thought about and why they don't work, which makes us think that this problem is unsolvable. Okay, so the first approach takes the idea that, like ultimately in RL, at least in the learning setting, we just care about learning a good policy, right? And the reason we use, and when you have F1 and F2, one of them is Q star, then we know that if you compute the greedy policy of each candidate function, one of them is pi star, right? So why not I just like get those policies and just throw away the value functions, right? And then what you need to do is essentially evaluate each policy on the data set you have to estimate their return and pick the one that has higher return, right? So, and this procedure is called off-policy evaluation. Okay, unfortunately, off-policy evaluation itself is a very difficult problem, right? The standard approach, which uses importance sampling, and this would indeed require full trajectory data, as Pascal has mentioned in his question. But even, and this will give you an unbiased estimate at the cost of exponential variance. Okay, I'm not going to the details here, but I'll be happy to discuss if you have questions later. So alternatively, if you don't want to pay exponential in horizon dependence, you can use standard methods that are inspired by either approximate dynamic programming approaches, TD methods like FIT-Q, or recently popular methods based on approximate linear programming ideas. But the problem is that in either case, you avoid exponential variance at the cost of requiring additional function approximation. And I'll actually come back to this point a little bit later. So this additional function approximation assumption is really problematic because it says that, I just want to figure out which one of these two functions is better. And you say you need a whole other function class to do this. And in the practical scenario, this is also very problematic because if you think about hyperparameter tuning in offline RL, right? So you say, okay, to do hyperparameter tuning, I need to have this entire function approximation separately, but who's gonna tune that function approximation, right? So essentially, to tune hyperparameter for tuning, for training, you're asking me to, tune hyperparameters for evaluation, right? So essentially, that creates a very weird chicken and egg problem. Okay, so
maybe I ask a question here.
Yeah,
so
go ahead.
Here, this extra hyperparameter tuning, is it of the type of problem that is kind of we know how to do it, like in the supervised learning setting?
No.
Or it would be different that
So basically you end up with the following problem that says, let's say we use FIT-Q to evaluate each candidate policy, but FIT-Q requires you to choose a function approximation. Say you need to determine your neural network architecture. Now you end up asking which of the neural network architecture would help you evaluate those policies most accurately. Looking at whatever you have on the data, they don't directly tell you that, right? Nothing in the statistics in the data, even if you're not overfitting. If you look at the training law of the TD, like the TD error, none of them directly tell you which one is better, right? So that's the kind of issue that I'm talking about. Yeah. Okay, but it turns out that our approach actually gives you an interesting way to address this question as a side product, but I'll get to it if I have time. Okay, so it turns out that it seems like we can't really solve the problem at the policy level, which is very different. So it would be better if we can solve it, but we can't. So we come back to the value function level, right? So we don't throw away the value functions, we work with them. And in this case, we know that one of them is Q star, and Q star obeys the Bellman equation. It's a fixed point of the Bellman equation, right? Q star is equal to TQ star. So a very natural idea is called Bellman residual minimization, which is to say, let's see how much each candidate function violates the Bellman equation, right? We just take the difference between the left-hand side of the equation and the right-hand side of the equation, and use some norm that is friendly to data estimation. Here I'm using the data weighted true norm, but you can also think of other norms. So the problem is that this Bellman error is infamously not amenable to statistical estimation. And this is one of the most infamous problem in maybe value-based RL, and has been discussed in depth in the new edition of the Sutton and Bartle book, right? So, and the reason is because the most naive estimator you can think of is this, sometimes we'll call this one sample estimator, right? And this estimator makes sense because the reward plus gamma times the value of the next state, if you take conditional expectation of it, condition on the current state action, is precisely the Bellman update evaluated the current state action, right? So at the first glance, it's very close to what we are trying to estimate. However, if you actually calculate this expectation, it turns out that in addition to the Bellman error term that we want to estimate, it actually contains an additional variance term that differs from function to function, okay? So there's a very weird overestimation term. People have thought very hard about how to get rid of this term, right? So one of the oldest solution is called double sampling, proposed by John Baird. But the idea is that you need to generate two IID random next states from each state action pair, which requires access to a simulator, which we don't have access to in the batch learning setting. So there's also debiasing approaches, for example, famously proposed by this paper by Antosh and others. It requires additional function approximation and is relatively complicated. So there's also the idea of using some form of projected Bellman error, which I'll actually come back to a little later. But if you use it in a sort of straightforward manner, it also requires additional function approximation. The last resolution is to say, hey, look, like this additional variance term is actually zero if the environment is fully deterministic. Okay, so some people say, okay, I only worry about deterministic environments. So maybe this will be a great method because I can just directly use the one sample estimator. It turns out that empirically we have shown that the method we propose can be vastly better than this one, even in fully deterministic environment, which is very interesting. I didn't, and it was pretty surprising, but hopefully I'll be able to get to it later. Okay, so, and these are the reasons that say why we thought that this is impossible, right? And in fact, because, validation is essentially training without optimization difficulties, this difficulty is also related to, you can reframe it as a question you can ask for training process, right? So in that case, it becomes this following open problem that asks, can we do offline learning in batch RL with polynomial sample complexity that only requires an exploratory data set and the so-called realizability condition, right? So I have a function space that contains Q star. And it turns out that all existing algorithms, especially those based on approximate dynamic programming, require stronger assumptions on the function space. And there are well-known counterexamples that show that ADP algorithm that use bootstrap targets diverge on their realizability assumptions. And so that's why we think this is impossible. And indeed, in the recent 1-2 years, there has been several works that actually develop information theoretic lower bounds for this problem, although under relatively weak data assumptions. So now eventually I'm getting to what we do in this work, right? So what we do is actually we show you how to actually break this conjectured hardness and using a reasonable data assumption. So how do we do it, right? So the theoretical basis of our approach is, again, we're still considering Bellman errors, right? So we just say, okay, one of them is Q star satisfies Bellman equation. So we want to see how much each function violates the Bellman equation. Now the Bellman error itself cannot be estimated from data. So alternatively, what you can do is to consider the so-called projected Bellman error, which you can estimate from data and is heavily studied in the literature, right? So the difference from before is that previously we just have F minus TF, but in this case, because TF is the problematic part and you can have a good estimation of it, what you do is that you project TF onto some function space G. Okay, so this big pi is the projection operator, and G is the function space that you choose to projection TF onto. And once, as long as G has bounded capacity, statistical capacity, you can easily show that this whole quantity is amenable to statistical estimation. Okay, however, because we introduced this additional G function class, it turns out that this entire projected Bellman error quantity is not always a good surrogate for whether the candidate function is equal to Q star or not. Okay, so this G function class need to satisfy additional assumptions for this projected Bellman error to be a good surrogate. And in particular, one set of sufficient conditions is the following. Okay, so it contains two additional assumptions. So first, your G class must contain Q star, or at least approximately, right? And that makes sense because when you plug in Q star, you want the whole thing to be zero, right? So you have Q star minus TQ star is just Q star. So you have Q star minus projection of Q star onto G. So if your G doesn't even contain Q star, you get a non-zero value. So this is like definitely needed. The second condition needed, or at least the sufficient condition, as proposed by Jeff Gordon, and also their related work by Chaba, Van der Rohe around the same time, is that this G class should be a piecewise constant function class, right? Essentially corresponding to some kind of state aggregation. And alternatively, you can think of like you have some fixed partitioning of the state action space, and you only consider functions that are that stay constant within each region of the partition. And the reason is that this function class is particularly good is because a lot of the analysis in RL we do rely on the contraction property of the Bellman operators. But if you combine it with projection operators to function spaces of arbitrary function classes, it often breaks this kind of contraction properties. But the piecewise constant function classes are a particularly nice and stable kind of function classes, such that when you combine it with the Bellman operator, the contraction property does not get lost. Okay, and this kind of thing is also heavily studied in the state abstraction literature. Now, this whole thing is pretty promising, except for that you now need to, hand me this G function class, which has these three magical properties, right? It needs to have bounded capacity, it needs to contain Q star, and needs to be piecewise constant, right? So, and in the context of a piecewise constant function class, the statistical capacity of the function class is roughly speaking the number of partitions you get, right? If you partition your state action space very coarsely, then as you can imagine, each partition will get a lot of data, and then you can estimate things there very accurately. So what we do in this work, the core idea of our work is I will show you how can we create this G class basically out of nothing. Okay, we don't require this as an additional input from the user, but rather construct it automatically from the functions from the candidate functions. So before showing you that, I'll first need to answer a question is, so I talk about I need these a nice function class G that satisfy all these nice properties. The very first question you need to ask is, does this kind of nice G always exist for any MDP? Or do I need to make additional structure assumptions on the MDP for this G to even exist, let alone like identifying it or constructing it out of nothing? Well, the good news is that this function class always exists up to small errors. And the reason is very simple, right? So suppose I have this, suppose I know the Q star of the problem, okay? So as illustrated here. And what I can do is that essentially I can just partition this state action space according to the Q star value accordingly, right? So the first thing I would do is that I'm going to discretize the output of Q star, say up to some epsilon discretization error. And that's why like you now see that the Q star is like a step, takes the shape of step functions. And then I'm gonna just cut the state action space into many small pieces, but I will be able to aggregate those pieces whenever the Q star value after discretization is the same. Okay, And if you're someone who works better with code than figure, this is like a one-line code of how to do this aggregation. And very easily, you can see that the number of partitions you end up with is always upper bounded by 1 over epsilon, where epsilon is the discretization error, right? And the reason is because basically each state action pair gets mapped to an equivalence class, where the identifier of the equivalence class is basically the discretized value of Q star, right? And since after discretization, the value that we are only considering like a single real valued output bounded range. So the number of possible values you can take is just 1 over epsilon. And this is true regardless of how complex the underlying MPP is, how unsmooth the Q star is over the state action space, and so on and so forth. None of those matter. Like I always get this very nice result.
So just a question though here. So, but your partition is Q star dependent, which you don't know, right?
Yeah, exactly, right? So that's what I put at the bottom. So this observation I've had a long time, but I always thought that this is completely useless, right? So the whole point of like having these function classes is to learn Q star, but now you're telling me that I need to use the knowledge of Q star to construct them. That's completely meaningless, right? Except we're actually now almost getting almost to the solution of the original problem. So let's come back to the original problem. We have two functions, f1 and f2. One of them is Q star. We don't know. How do you find it out? Simple. You just partition the state action space according to both functions simultaneously, right? So as we did before, you first discretize both f1 and f2 up to a small discretization error, partition the state action space accordingly, and aggregate all the state action pairs whenever both functions stay approximately constant across those states or state action pairs, right? And because one of them is Q star, by doing so, you guarantee that the resulting partition can always express Q star, right? Approximately. And again, this is the code. And in fact, this is like when we actually implement this method, this is roughly what we do in our implementation. And the cost of doing this without knowing which one of the functions is Q star is that in this case, you pay 1 over epsilon squared. But this is still, theoretically speaking, affordable. And as we'll see, like in practice, it actually works very well. And some people, like when they say this, like they say 1 over epsilon, they kind of think of like non-parametric regression. But I want to emphasize that this is not really non-parametrics because we're not assuming any kind of smoothness over the state action space. And we're actually discretizing according to the output of the functions, which is fixed dimensional, right? So here we're considering two functions. So this exponent on 1 over epsilon is always 2. It's never going to be bigger. And in this case, to complete the story, what you do is that you create this partition, which implies a piecewise constant function space, and you use the projected Bellman error associated with this space as G to identify which of your candidate functions is a closer approximation of Q star. So this is very nice. However, we're definitely not satisfied with just merely 2 candidate functions. In hyperparameter tuning, you may want to compare, dozens or hundreds of different models. And even more, maybe at some point we want to extend this to training, where you need to worry about, even possibly continuous function space. So in order to overcome those challenges, we have to ask, can we extend this method to large function classes? Let's say for now, finite but exponentially large function class. Well, if you just repeat the procedure that I just did, but in this case, simultaneous partition the state action space according to all functions in the function class, then that's actually very problematic because now you really run into curse of dimensionality because the number of partitions you get is 1 over epsilon to the power of f, the number of functions you have. So this whole thing is going to be essentially super exponential, right? It's doubly exponential in what you want to afford, which is the logarithmic dependence on f. So this brings us to the very last trick we have, which actually overcomes this difficulty by doing a tournament procedure. So what we do is that essentially we never run the previous procedure on functions of on more than 2 functions. We only apply the previous procedure on pairs of functions. And when you give me a large function space, what I'm gonna do is that I'm gonna take every single pair of the functions and run the previous procedure, okay? So essentially it's kind of like having every pair of functions fight with each other and figure out which function actually essentially like wins most. The expression here, again, like you have the minimax form where main f, you can think of it as the candidate function being examined. The inner max f prime is the function that together with f create the piecewise constant function class G. So in this case, the G is has a subscript f and f prime. And the objective again is the projective Bellman error. So one difficulty here is that the previous analysis assumes that one of the compared functions is Q star, right? But when you're dealing with a large function space, maybe only one of them is Q star, and all the others are bad functions, right? So a lot of the comparisons are between the bad functions, which our previous analysis do not give any guarantee to. But fortunately, it turns out that for this analysis to work out, we don't even need to care about those comparisons. We only need to care about the comparisons where at least one good function is involved. Let's say Q star is involved. And I don't think I have time to get into details, but roughly speaking, when Q star is being examined, it never sees a large error. So when you take max over all the competitor f prime, your loss is always small. However, when you have a bad function and when you examine it against the Q star, it will be enough to expose the deficiency of the function. So you get a big loss. And when you take a max, that big loss always translates to the final score of the function. And then when you take arg mean outside, it will help you identify Q star. Okay, so this is like a very rough proof sketch. And we have a sample complexity guarantee that for the realizability assumption can be relaxed to handle small approximation errors. And there's a C parameter that characterizes how exploratory the data set is. There's some open questions on that, but otherwise it's a very standard kind of guarantee you will see because it has polynomial dependence on 1/epsilon, the horizon, the C parameter, and the logarithmic dependence on the number of functions. Okay. So there are some open questions about which kind of definition of C you can have. I don't think I have time to go through that. And again, I'll skip the sort of proof sketch and analysis unless someone is interested and want to ask later. What I want to get to in the maybe remaining 5 minutes or 10 minutes or so is to show you some empirical results, okay? So first of all, this algorithm is purely information theoretic, right? So if you actually give me a large function class, I will need to do double enumeration. So as far as I see now, I don't see how this can be directly used in training. However, we can already test it empirically almost out of the box for the important problem of hyperparameter tuning that I just mentioned before, right? Because in hyperparameter tuning, they're always working with a finite and a discrete hypothesis class that you can afford to enumerate over. So this is what we do. We just basically implement as is and also directly throw it in not only like GM control problems, which have continuous but low dimensional state space, but also like high dimensional pixel observation Atari games, right? As you can see in the top row. And we compare it with a couple of other hyperparameter free heuristics, some of which are used in some application papers. And so here we're showing regret, which is the lower the better. And the purple, the red curve is our method, and purple is the skyline. And you can see like they just perform like much better than the alternatives. And as I mentioned earlier, some of these environments are fully deterministic, especially in some of the GM environments. And in those cases, in theory, the one sample estimator that I mentioned at the beginning of the talk should work. But actually, like in many of those cases, the one sample estimator, which is this orange curve over here, is actually much, much worse than what we can achieve. So I think that's an interesting question to ponder on theoretically. And as I mentioned before, the dominating approach currently for hyperparameter tuning is to reduce to off-policy evaluation. But off-policy evaluation needs additional hyperparameters, right? So what we do is that we compare to a canonical representative method, fitted Q evaluation, as a baseline, and we consider we'll compare their sample complexity with our method. So here, these two figures are showing regret as a function of sample size. And as you can see, at the limit of really, really large amount of data, we achieve similar performance with fitted Q, but fitted Q is way, way less sample efficient compared to our method, right? And I also want to mention that, in fitted Q, you need to choose a neural network architecture. No one knows how to do that. So what we did is that we just cheated, okay? We just look at all the training architecture and figure out which training architecture give you the best policy, and we use that architecture to do evaluation. And the reason of this difference in sample efficiency, I think it really highlights the fact that when you use off-policy evaluation method like fitted Q to solve hyperparameter tuning problem, on the validation set, essentially you have to resolve the representation learning and perception problem from scratch, right? Because you're still dealing with like high dimensional pixel observations as your inputs. You need to figure out how to compress that down to good features that allows you to predict the performance of each policy. Whereas our method, BVFT, as you can see before, the kind of representation we use have at most complexity 1/epsilon square. So it's actually bounded regardless of how complex your underlying MDP is. So it doesn't really care about like how complex your problem becomes. And that's why it scales much better in terms of sample efficiency. Okay, so I think, so one last thing I would mention is that our method works directly very, very well on, say, Atari games with discrete action space. And it turns out that in those cases, standard algorithm actually gives you a very good approximation of Q star. But in continuous action problems, where typically you would run something like an actor critic algorithm, existing actor critic algorithms usually give you very poor critic functions. Despite that, somehow magically, they can always give you a good policy. So if you directly take the critics and feed into our algorithm, that actually doesn't work because those critics are just far, far away from Q star. So what we end up doing is that, okay, we say, okay, those value functions are poor fit. So we can use OPE algorithm to refit the value function. But again, we run into the previous issue that, no one knows how to tune the hyperparameters for OPE. And so it turns out that you can slightly modify our derivation and it will be directly applicable to value function selection for policy evaluation as well. So all you need to do is you see here, the entire algorithm is the same, except that you replace the optimality operator with the policy evaluation operator. And roughly, and the entire guarantee almost extends, the proof almost trivially extends. So roughly speaking, what this gives you is that for fixed policy pi, if you give me multiple functions, and one of them is a good approximation of Q pi, the variant of our algorithm can figure that out. And we show that indeed, when you use OPE to do our policy evaluation, but you're not sure how to set the hyperparameters for an OPE algorithm, you can use this method to tune the hyperparameters of OPE, and actually gives you, always gives you the automatically identify the optimal OPE instances out of the different OPE hyperparameters. We'll also have some additional OPE experiments. Okay, so I think that's roughly speaking all I have today. And again, thanks for coming, and I'll be happy to take questions.
Yeah, thank you very much. It was a very interesting talk. So we have, I think, several minutes for questions, and also for people who joined later, we have a roundtable after the talk. So from 12 to 12:30. So stay around if you want to chat with them.
So I have a question here. So when you described earlier how, I guess, checking the error with respect to the Bellman equation is not convenient because we have a sample, and then otherwise the value function is itself a mean.
Right.
So there is this line of work on distributional reinforcement learning, and I must say here that within our group we've read many papers, and then we've had many discussions about this. So would the problem become easier if instead of comparing two Q functions, you were given two distributions over Q functions? And here the intuition is that if you have distributions, the fact that we have a one sample, then one sample you can easily estimate its likelihood.
Likelihood, okay.
To the distribution. So I guess this is a high level question, and yeah, I'm not sure what your thoughts are about this.
Yeah, I haven't thought, I think that's a very good point, right? So if you can estimate likelihood, that's maybe amenable to one sample estimation. I'm not sure. I'll be interested in figure out. So, but I would still doubt, because I think that the key, the key thing here is that you have this. So at least here, the real problem is that you have conditional expectation inside the square, right? But what we can estimate is expectation outside of the square, right? So you don't want something that is conditional expectation inside square. So for the distributional setting, I guess you still, like, whatever your model is still predicting a conditional distribution, conditional state action pair. So somehow, like, you need to be able to somehow, like, either use Jensen or something that take that outside of the either square or something, you know, like from individual state action level to the population level. So I haven't thought really deeply about it, but I think I came across this before, and my vague impression is that it's not trivial either. But I could be wrong. I'd be happy to take a deeper look at this later.
Okay, very good.
Yeah.
Okay, thank you. I have to run to another meeting.
The other thing is, sorry, Pascal, let me just mention another thing is, I think it's actually more fundamental, is that in distribution RL, you predict the return, right? You predict a distribution of returns. But as I mentioned earlier, you don't get direct samples of the optimal return.
That's
right.
True.
So you can't directly plug in, you get state, you don't get the discounted sum of rewards under the optimal policy. So you can't directly, like, plug that in. I think that's another maybe more basic difficulty.
Yeah, that's right. So yeah, so that problem remains no matter what then.
Right.
Okay, great, thank you.
Yep, thanks for coming, yeah.
Other questions?
Great, thank you everyone. And Amir Masid?
Yes. Do we want to finish now, or do we want to move towards a roundtable?
It's up to you guys, whatever you want.
Right, yeah, I guess we can stay around in the same channel for people who want to stay and ask more questions. So, yeah, so anyone who basically, yeah, I guess we are almost done with the usual time for the talk.
Yep.
So thank you again for your talk. It was very interesting and I have a lot of questions, so I will stay around. And, but join me in thanking Nan for his excellent talk.
Yep, thank you.
All right, so I think we can call this now roundtable for the next half an hour. So I think it would be good if you are participating, turn on your video so it feels more like a
if people want to show up their faces, that would be great.
Yeah, it would be good to have at least a few people. But maybe I ask questions so until people become more comfortable. So okay, I have several questions, but the question, So you have this G operator, which basically takes F1 and F2, or F and F prime, and computes the kind of the joint partition of those functions, right?
Exactly, yeah.
So I understand how it works in like simple cases, but if you have, I give you two neural networks, for example, how do you compute the joint partition? And
so here, I think that's a great question. I think that the key here is to realize that we're comparing. So let's say you use two different neural networks to do training, right? And at the end of the day, you get one function from each network. So what you're essentially doing is that it's just like in supervised learning, you're taking those specific functions to validation. You're not taking the entire neural net to validation, right? So that's the first thing. And the second, these functions, I mean, in practice, they will still be represented as neural nets, right? So you may wonder, like, does that actually introduce any difficulties? So it turns out that, so if you look at the equation here, right? So we all know that the projected Bellman error is essentially, in the first line here, it's just a regression result of this square loss real valued regression problem, right? So actually it turns out that what happens is that you have your validation data set that you're using to run our algorithm, right? So essentially what you really need from the candidate functions is that all you need is to evaluate the function on all the states that show up in the data set. You don't need anything else, right? Because when you evaluate the candidate function on each SA, that tells you which SA you need to aggregate together.
I see.
Right? And because projection onto the piecewise function space is really like you just take the outcome and take the average across data points in the same region. So you just mark, these data points need to come together. These data points need to come together. And you look at their one sample Bellman update, you take their average. That's it.
Okay. I see. Yeah. So essentially you don't partition. You partition based on the empirical measure that you have.
Yeah.
Okay. Yeah. So that's interesting. Let's see if there.
Yeah, actually, we have in the follow-up empirical paper, we have a explicit calculation of how many arithmetic operations you need to do. Like everything is closed form. You just need to enumerate over all pair functions. If you have something like a neural net, the most computational heavy thing you do is to evaluate the neural net on states. That's it. You don't need to do anything else complicated on the neural nets or whatever.
Okay, that's interesting. So, I don't know. I mean, do you have comment or question, or should I keep asking questions? Because I have enough questions.
Go ahead.
Okay, so ask one more question now. So I think the early slides, basically you said the reason that you argued for piecewise constant function was because of essentially aggregation. It would be contraction, but I don't understand why this is needed. I mean, for results, a fitted value iteration. So you have.
I think what I said is that this is a sufficient condition. It's not necessary. It's not always necessary, right? It's one set of sufficient condition.
Okay, but you don't even need like a capital pi t to be contraction, right? For your arguments?
Excuse me. Capital pi, I think I need it. I do think I need it, right? Because at least contraction would be sufficient, right? Because if it's a contraction, then, so here's the thing, right? So if your G class only satisfies realizability, then if you plug in Q, it'll always be 0, right? So the Q star is always a fixed point of the projected operator. But the problem with general G class is that this fixed point may not be unique, right? There may be other like arbitrary bad class that, when you do a Bellman update, it becomes very different. But for some reason, when you project it projects back to the same function again. So the contraction, what contraction gives you is that it gives you the uniqueness, right? Like,
okay, I see.
Right. So just like under the normal T operator, the fixed point is uniquely Q star. So here, because pi G T is again contraction, so we know that Q star is a fixed point, then Q star is uniquely the fixed point.
Right. Yeah, I guess I wasn't thinking about uniqueness, like, because the way I usually think is that the issue is divergence, not
right? Yeah,
not
I guess
multiplicity of fixed points.
Yeah, I think think about uniqueness and divergence in the same picture. Sometimes it's a little bit tricky, but one way I think of it, which is maybe not ideal, is that like one way to avoid divergence is to have a bounded function space, right? And then you never diverge. But actually, I think what happens is that when you have a bounded function space, on the boundary, you have those points where you want to go out, but you're not allowed to, you come back. And then in those cases, the projected Bellman error can actually be small.
Okay, right, yes. But those are not the points that you, okay, yeah, okay, makes sense. Okay, that's.
I have a question.
Yeah, go ahead.
So in the tournament process, you described, imagine the comparisons. So you will need to do order of size of function class number of comparisons.
Well, you need to do that square number of comparisons.
F squared, but if you do it like an actual tournament, you may be able to do it.
You may be. So I think even that is unclear, right? Because one issue, so I guess what you're saying is that maybe you first divide candidates into groups, run things in a group, and then aggregate them, have later like semifinals, finals, and eventually.
Yes, exactly.
So even that is we thought about that. We actually run into related problems in practice because when we do cross validation, we need to enumerate over all pairs of functions, right? So it's affordable if you have like say tens or 50 models, but if you're comparing like say a few hundreds of models, the square is still computationally quite heavy. So we thought about that. But one issue of that is that in these tournament-based algorithms, having the more levels you have, the later levels can actually have degenerate performance, right? Because the reason is because you're not just comparing things based on a absolute metric, right? So because you're doing these pairwise comparisons, the metric, the objective function, depends on these G class, which are created from the value functions. And what the analysis shows is that the better the value function, the better the quality of the metric that you're using. So what can end up happening is that maybe in the first round, let's say you have Q star and something that is a close approximation of it, but not nearly as good. So if you run them in the first round, maybe you throw away Q star, but you keep the lesser approximation. But once you lose Q star, you only have the lesser approximation. In the next level, the best quality metric you can provide it is like capped by that bad guy or slightly worse guy. And then then every level, like things can slightly worsen a little bit. So we haven't done a careful analysis of this, but I actually, a few years ago, I had a related paper on tournament selection over state representations. And turns out that in that case, if you do multiple comparisons, things actually get exponentially worse with the number of like kind of like layers you have. So it's unclear whether that will be a practical problem, but it'll be interesting to figure that out.
All right. And also, can you bring the final theorem again? Was it about the computational complexity?
No, this is the sample complexity. Sample complexity, yeah. So because this work we're mainly focusing on sample efficiency, and because like as mentioned for cross validation, like you don't really care about computational complexity that much because everything is finite, and also as I mentioned, when you have a finite function class, all our computations are actually closed form. You don't have any like fancy optimization to do here. Like everything you do is like just I think all you need is plus minus multiplication, like very basic arithmetic operations. And other than that, it's just evaluation of the candidate function on the data points you have. So computation wise, it's quite simple. But we're thinking how to actually apply this to training. Where there, like computation will be a very, very major challenge because this objective doesn't seem very friendly to optimization at all.
Right.
Okay. So are there, yeah, I guess it still doesn't feel completely like a roundtable. And that's a kind of the challenge with online presence.
I have another question. Like you said that you at first published a paper saying that this problem can be impossible. So what was the reasoning back then, and what was the?
I think the reasoning. So the reasoning is that basically, like I've given like two common approaches, and neither of them directly works. But you may think, okay, maybe we just haven't thought about other approaches, which turns out to be the case, right? But I think the intuition is that if you think about the problem, the setup is really minimal, right? How many symbols you can manipulate at your hand? There's F1, there's F2, there's S, A, R, S prime. Okay, so whatever you write down, it depends on these 6 symbols. And I think there was a strong sense that we have thought about every single manipulation we could have around these 6 symbols. Who would thought that you need these kind of like partitioning kind of operation? I think anything that's smooth, roughly speaking, we have thought about, and they just don't work.
So you basically just check these common attempts you mentioned, and there were no lower bounds or anything.
Yeah, actually, so we tried to prove some lower bound in an earlier work. Didn't quite work out, and I think the reason is that there's an upper bound, and but there is some recent lower bound. Actually, we also have some work in it. So the references here, I can give more specific references here. But the commonality of the lower bound is that they require relatively weak data assumption. And actually, and in our, so I think the first lower bound, and this is the work by Wilson Wang, Dane Foster, and Shamkagade, they worked it out for the finite horizon setting. But later we have a 2-page short note that simplified it for infinite horizon discounted setting. Turns out that infinite horizon discounted setting, that lower bound just becomes like 2 states. It's a very simple MDP, but it actually tells you that the kind of data assumption they assume actually gives you unidentifiability. Actually, that lower bound is infinite sample complexity. Like even with infinite data, you can't figure out. So I think what that lower bound is that the kind of data assumption they assume, which actually seems quite natural from a supervised learning and bandit point of view, is just not appropriate for long horizon RL. So you need something stronger. And indeed, our upper bound relies on substantially stronger data assumption than theirs.
So I was thinking, okay, so one of the few approaches that you talked about in the beginning, I think you didn't talk about learning a simulator for.
Oh yeah, that's a great question. So
do we have those things like exponential growth with horizon or?
No, so I think so I think this is twofold, right? So so first of all, I've been focusing on value-based RL in this case, right? And what I'm assuming is that I'm given these 2 candidate value functions, and that's basically all I have access to. So if you need a model, you need a separate model class. But I think it's a good question is that you can think of, well, can I ask the question at the model-based level, right? If I have model M1 and M2, I need to select one of them. Well, clearly you can just do MLE and that will work, right? But there is something, I think there are multiple things that are tricky about this. First, if you have 2 models and you assume that one of the models is the correct dynamical model, that's a much stronger assumption than you have 2 value functions. One of them is the correct value function, right? And in particular, when you have a realizable model class, you can actually get the low inherent Bellman error assumption on value function class automatically. Because what you can do is that you can do this this minimax thing in Antosh and Chaba and Remy's paper. I know you and Chaba, you also had a later paper that does similar things. You can basically do these things because what you can do is that you can just take all the models, ask each one of them to spit out its optimal value function. Okay, now you have a realizable value function class. Now for this G class, what you want is that you want to be able to model the Bellman update of any function in your value function class. And what you can do is that you take that value function class, you take each function and pair it with each model, and use the Bellman operator in that model to update the value function. Okay, you get another class that is this G, and then you can run minimax. Okay. So this is the second point. The third point is value model realizability. I think of that as a very, very strong assumption. And the reason is because you need to, in value function, what you need to predict is a single scalar value, right? But in model, you want to predict an entire conditional distribution over states. And this is a horribly complex object when the state space is very high dimensional, right? Mm-hmm. So that's why you see like a raw models, dynamical models are only using RL for like mostly like, the control problems with relatively manageable size state spaces. And in say pixel observations, I think even those so-called model-based approaches, what they essentially do is that they need to map the observation down to some latent state space and learn a model in the latent state space. But the entire approach, actually, you can no longer do something like MLE, but rather what you typically do is that you actually use that model to unfold a few steps and use like TD-like losses to model that, right? So I would say those approaches are really like value-based approaches with a model-inspired architecture, right? Okay, yeah. And actually I have one more point on that. So let me finish. Is that I've also thought about this like there's a related problem here, which is very interesting is suppose you're doing model-based RL, but you want to learn these like latent models over different representations, right? So essentially each candidate model is not really just the dynamics. It's first is an encoding of the raw observations to some low dimensional things, and different models have different encodings. And then it's a dynamical model over the latent space, right? And in this case, if I give you two models like this and ask the same question here, I think you wouldn't be able to do it as straightforwardly because each model is predicting completely different things, right? I'm predicting the next, like my encoding of states, you're predicting the next, your encoding of states. You can look at the MLE, but those two things are just not comparable.
Right, yeah, I guess if you only compare in the latent space and there are two different encoding.
If you have different representations, then you're not even comparing the same thing, right? Unless everyone already agrees with a predetermined representation, then yes, everything is comparable. But so actually, I think that's one of the problems that motivated me to think about this problem, because even in those cases, you can first do planning in the models to get the value functions. And then once you're at the value function level, everyone agrees that the output must be single dimensional, scalar valued. It should represent Q. And regardless of what your latent representation is, you can throw in this algorithm here and have them fairly compare with each other.
Well, I guess you can say that, I mean, the model that only first we do encoding and then learn the model in the latent space is like not a complete model, because there should be also a decoder that moves us back to the observation level. And if that would be the case, then you can do comparison or maximum likelihood.
Yes, if you ever go back to the raw observations, yes, you'll be able to do it. But you're not required to do it in the model-based case, right? Because you can just plan in the latent space and spit out a policy based on that.
Yeah. So basically, we need to somehow be grounded in.
Yeah, exactly. So yeah, exactly. The issue here is that if you just project to the latent space, there lacks like a grounding.
Yeah. Okay. Yeah, I guess that makes sense. So, anyone else wants to participate, ask question about life in academia, what you should do to be successful? I don't think it needs to be about necessarily this research.
I guess so, just stop sharing.
Yeah, okay. I mean, if, so maybe one thing, if they're not, if there is no other question or discussion, maybe we can have a 5 minutes break, and then we can start the individual meetings afterward. Is that good for you?
Yeah, sure. I guess after this is, oh, okay, I see.
Yeah, it would be with me. So
sure.
And so just 5 minutes, and then we can start maybe at 25 or something like that.
Sure. Yeah. Will it still be this Zoom meeting?
I think it is the same link.
Yeah, I don't see other links, so I assume it's still this one.
So there is a Zoom registration down there, but the link seems to be exactly the same as far as I can compare.
Yeah,
so
then maybe just use this one. Yeah,
we stay there.
Cool. Okay, so
see you in 5
see you in 5 minutes. Yeah.
Okay.
Thank you.